All right, folks, it's your old pal, John Frensley again, and this time we're going to do the AP Physics 1 free response questions that dropped yesterday. It is Monday morning, and these came out on Sunday afternoon, so I have had a chance to look at them. So hopefully I won't make a bunch of mistakes reading it completely cold like I did for the Physics C ones. But first, just a reminder, World's Finest Physics is my brand. You can see the website there, and we provide tutoring services for students, but also professional development for physics teachers and math teachers. And you can see all those offerings at that website. Okay, so let's have a look here. So what we've got here is we've got a block released from point A, 6R. After being released, the block slides down a track as shown. And when released from point A, the block does not lose contact with the track at any point. B and C are located at the highest points of the respective circular ramps. Both the radius are. All the frictional forces are negligible. Okay, so apparently we're going to start having energy bar charts on the AP exams. And apparently we're going to start having bolded task verbs on the AP exams. You see that in the new CEDs, and they did it here. So apparently that's how we're going to do it from now on. Okay, diagram A shows an energy bar chart that represents gravitational potential energy of the block Earth system and the kinetic energy K of the block at point A. 1, 2, 3, 4, 5, 6. So each bar basically represents an R worth of height. Okay, draw shaded regions in diagram B that represent the gravitational potential energy of the block Earth system when the block is located at point B. Well, thanks for telling me it's a height of 2R, so I don't have to flip back to the previous page. So the height is 2R. Let me just double check that's the case. Yeah. And so the kinetic energy then will be the rest. And so it looks like drawing energy bar charts is going to be something that they're going to ask us to do, but they're going to have to give you like a long set of instructions on how to do it. So what I would do is kind of internalize, if you're a physics teacher, how they want to do energy bar charts on the AP exam, then practice the students on exactly that way in class. And then they don't have to read all this when they're in the middle of the free response. Can save them some time, okay? Let's see. And then it looks like they give them one of them as an example in each case. Storing conservation of energy, derive the expression of the speed of block at point B. Expression answered in terms of R and physical constants. And it looks like every time from now on that there's the word derive, there's going to be this sentence. Begin your derivation by writing a fundamental physics principle or an equation for the reference book. So this would be conservation of energy. Conservation. Oh, well, they even said that. Energy, right? So it's going to be maybe mg, the height at point A, plus 1/2 m, the velocity at A squared, equals mg, the height at B, plus 1/2 m v at B squared. This is awfully nice of them to start with that. I mean, anyway. The mass are going to cancel out. The velocity at A is 0, and so we get g times 6r is equal to g times 2r. That is point B, isn't it? 2r is high? Yeah, it is. Okay. And then plus 1/2 of velocity at B squared. So then this is going to be 6grs equals 2grs plus half of VB squared. So then 4grs are going to equal half of VB squared. And then 8grs is going to equal VB squared. So then VB is going to be the square root of 8grs. All right. Well, whatever. All right. On the following dot that represents the block, draw and label the forces that are exerted on the block when it slides past through point C. Need to remember what point C is. Okay, right there. All right. So this is something that the new CED makes very clear. So listen carefully if you're a physics teacher. If there are two forces pointing in the same direction, and there are here, there's an mg force of weight and there's a force normal, you need to teach your students that they need to draw the arrows side by side, not overlapping. So like this is not going to cut it. Don't do this anymore. Stop your students from doing it. I also know from my time reading the AP physics exams that if there's a little gap, we don't take it. Okay, so don't let them. There can't be a gap. The ink or pencil has to go all the way into the black, and they have to be side by side if there are two forces in the same direction. One thing I found, or one thing that they've promised, and I know what a College Board promise is worth. They say that if there's two forces in the same direction, they'll try to put an extra large dot to make it easy to put it side by side. But I've seen them not do that in the past. So, okay. A student claims that 4r is the minimum height that point A can be so that the block can slide through point C without losing contact with the track. Okay, so this, oh, okay, I see what they're getting at. This would be the 4R they're talking about. So in other words, if you release the block here, then it could make it past point C without falling off the track. It could make it to point C, but then it'll stop and fall right out of the track, right? So briefly explain why this claim is incorrect. Reason why is if the block is released at height equals 4R, then upon reaching point C, also at height equals 4R, okay, the block will have no kinetic energy and stop. But there is a minimum speed. I happen to have it memorized. V equals radical GR. You can get that from circular motion. Required at point C to stay on the track or stay in contact with the track. So the release height must be higher to allow the block to have the needed kinetic energy at point C. Okay, that was a lot more than a briefly explained, but I want to make it clear to the reader that I really know what I'm talking about. Just warning for those of you who are teaching AP Physics 1 next year and AP Physics C Mechanics, this equation does not appear on the formula chart, but it does explicitly appear in the course and exam description. So students are going to need to be explicitly taught, maybe not memorize this, but explicitly taught how to handle the top of a vertical loop, because the top of a vertical loop is in the CED, like specifically, explicitly, right? Okay, what's going on here? A student ends a spring of unknown spring constant vertically by attaching one end to a stand, as shown in figure 1. The other end of the spring has a small loop from which small cylinders can be hung. In addition to the spring, the student has access only to a variety of cylinders of unknown masses, a stopwatch, and a digital scale. So let's read between the lines. What are they trying to say that we don't have access to? No meter stick, okay? T-I-C-K. It's the middle of the morning. I've not had my coffee. Okay, design an experimental procedure that the student could use to determine the spring constant K of the spring. In the following table, list the quantities that would be measured using only the provided equipment in your experiment. Define a symbol in the space below the table. Describe the overall procedure. How many students are going to write in the space? How many students are going to write in this space? Because I was fixing to, except I read this. So I bet you a bunch of students are going to write in this empty space here. Okay, use the symbols defined in the table. Okay, so I'm going to try and follow the directions the best I can. Okay. Oh, okay. Wow. Okay, really? Do you think we're this stupid that we have to be helped out this much? Okay, there's a meter, a mass, I meant to say, of each cylinder. That's going to be M. The time for 10 oscillations. If you just say wiggles, they'll know what they're talking about. I'm going to call that T10. And I think that's all I really need. Okay, so the procedure and diagram if needed. So I'm going to say hang a mass from the spring, pull it down a centimeter or two, and release. Okay, use the stopwatch to time 10 up and down motions and divide by 10 to get the period T of the motion, right? Timing 10 cycles reduces uncertainty. Does it say that? Like any steps to reduce experimental uncertainty, including steps necessary to reduce experimental uncertainty? Just so you know, I specifically said, like most readers, Well, I can't give the readers that much credit, but readers should be able to see, use the stopwatch time 10 up and down motion divide by 10 and be like, oh yeah, that reduces experimental uncertainty. I don't trust them that much. Okay, I've been into the reading. Okay, so I actually tell my students to explicitly say, this is what I'm doing to reduce experimental uncertainty. Okay, then repeat the procedure for each cylinder. Put each cylinder on the scale to get its mass. So we have a table of masses and periods, right? Okay, so all good. Well, friendly, you're not supposed to say draw a data table in your lab notebook. No, I didn't say draw a data table. I'm saying what the table's going to look like, right? Okay. Indicate, which means just answer the question. The quantities that could be plotted in a linear graph, the answer is going to be t squared versus m. I've done this about 8 times with my students by this point. We have a 2 week long simple harmonic motion unit. So they know that period equals 2 pi radical m over k. Excuse me. Okay. Okay. Here we go. Period equals 2 pi radical m over k. All right. So then period squared equals 4 pi squared m over k, which means period squared over m is 4 pi squared over k. And then what my students should say is they should say this is the rise, this is the run, this is the slope. But you want to make sure you say it in words also. Set the slope of t squared versus m equal to 4 pi squared over k. Solve for k. All right. In a different experiment, the student attaches one end of the spring to a force sensor, and the other end is attached to the cart. The student places a motion sensor to the right of the cart and pulls the cart to the right. A small distance, the spring is stretched. The student releases the cart from rest, and the cart spring system oscillates. The following graphs show the velocity of the cart and the force as functions of time. Yeah, okay, sure. Using the data and the velocity time graph only. Oh, here's what it says. Using the data and the velocity time graph, calculate the change in kinetic energy of the cart from 1/2 to 2. Okay, so from 1/2 second to 2 seconds, the change in kinetic energy. So the delta KE is going to be 1/2 m v at 2 squared minus 1/2 m v at 0.5 squared. Okay. Do we know the mass? It says 0.25 kilograms. And I did read this right. It's from 0.3 to 0, right? Okay. So this is 0. So you get negative 1/2, 0.25, 0.3 squared, 0.25, and 0.3 squared. Do I have a calculator handy? Yes, I do. Okay. 1/2. Okay. 1/2, 0.25, 0.3 squared. Okay. So the change in kinetic energy is 0.01125 joules. Okay, now let's look at the difference between these two task verbs. Calculate means that there's probably going to be a pretty exact answer. Estimate is like calculate, only there's going to be a much wider range of possibilities. Using the force time graph, estimate the change in momentum of the cart from 0.5 to 2.5. Explain how you arrive at your estimation. So I'm going to say change in momentum is the area of force versus time. And we're going to go from 0.5 to 2.5. So from 0.5 to 2. Well, that's not much of an estimate. The answer is 0. All right. Why is the answer 0? So the delta P is 0. I'm going to say this. The delta P is 0 since the force versus time graph has equal positive and negative area between 0.5 and 2.5. This is seconds. This is what I was imagining when they said estimate. Is I thought that they would actually like make me estimate like an actual area where I could conceivably do something like this, where maybe what I do is I make a set of triangles here. Like, let's say I'm going to estimate just this area right here. Okay, so look at what I'm trying to do here. You see what I'm trying to do here? I'm trying to divide this into pieces, maybe like so. And so what's the area of that triangle? It's going to be 1/2 of the base, 1/2 of the base. Oops, the base is 0.25. Okay. So half of the base times the height, which I think is 0.06. Okay. So 1/2 base times height. And so both of these are going to be 0.006 or negative 0.006 area. And then this has to be 0.012, both of these. And then this is going to be 1/2 base, and this height, which is 0.02, so 0.0025. So I've got twice 0.006 and twice 0.003 and twice 0.0025. So this area would be about 0.023. Again, that's an estimate, right? So that was the estimate that I was expecting. But no, there's really no estimating this. The answer is going to be 0, okay? Do the data from the velocity time graph confirm your estimation part C? Briefly explain. Okay, so at 0.25 and 0.5 and 2.5, it's the same velocity. So the velocity at time equals 0.5 seconds and time equals 2.5 seconds is the same. So the momentum is the same. So the change in momentum must be 0. So yes. Okay. You can tell I didn't look that closely at these questions before we were asked them. Otherwise, I would have known the answer to that estimate question already. Okay. The left end of a uniform beam of mass M and length L attached to the wall by a hinge. One end of the string of negligible mass is attached to the right end of the beam. The other end of the string is attached to the wall at point 1. The beam remains horizontal, and the angle is FH. That's the force the hinge exerts, okay? And the angle, the following rectangle represents the beam. Draw and label forces exerted on the beam, okay? So let's start with the obvious one. It's capital MG. There's also going to be a force tension, and the force of the hinge is actually going to be identical to this one. So in this situation, the tension force and the hinge force are actually identical. They even have identical angles, which I'm not going to draw the angle on here because I'm only drawing the forces here. But it makes sense, and I do teach this to my students, that in situations like this force tension and this force hinge are the exact same magnitude and angle. And the reason it only works for a uniform bar, because if you just draw this without the labels, you can see that this has to be in both rotational, because the torque's balance, and translational equilibrium. So the tension and the hinge have the exact same force, same angle, and it's worth your students knowing that. Okay. The string is then attached lower on the wall. The angle is theta 2. The dashed line represents the string shown in figure 1. Indicate, which means just give me the answer. The new force tension, I think, is greater than force tension 1. Justify your answer using qualitative reasoning beyond referencing equations. So what I'm going to say is I'm going to say this. I'm going to say that force tension 2 has the same vertical component as force tension 1, but since force tension 2 is more horizontal, force tension 2 has more horizontal component than force tension 1. So obviously did not want me to write that DBQ level essay for that there because there wasn't a lot of space. Starting Newton's second law in rotational form, derive an expression for the magnitude of the tension in the string. Well, sum of all torques equals I alpha, and alpha equals 0. So really the net torque equals 0, which is the torque clockwise equals the torque counterclockwise. Who is providing the clockwise torque? The clockwise torque is, I'm going to take the torques about this point. So then the clockwise torque is going to be mg times half of L. And then the counterclockwise torque is going to be provided by the force tension, which is L tension sine theta. So then when I solve for the tension, the L's are going to cancel out, and I'm going to get tension equals mg over 2 sine theta. And you may recognize that this is actually the solution to the hanging traffic light problem where you have mg and this, and you end up with the force tension is equal to mg over 2 cosine theta. Well, why is it cosine theta here and sine theta here? Because this is cosine theta. The theta is measured from a vertical line. This sine theta because we're measured from a horizontal line. So this is really the hanging traffic light. Hell, look at this diagram and then tell me that's the free body diagram of this extended body diagram. And by the way, College Board, it is called an extended body diagram, not a force diagram. You might want to edit your CED, extended body diagram, because it shows the extent to which the body occupies space. I didn't make that up. Eugenici Akina did, however you pronounce her name. Okay, whoever you are. Is your derived equation part C consistent with justification property? Yes. Okay, so what did I just say? Tension equals mg over 2 sine theta. As theta gets less, sine theta is less. If your students are not in pre-calculus and they didn't know that, they can just look here how it is that you go from 1 to 0.87. They do have a calculator. To 0.8, to 0.7, to 0.6, to 0.5, to 0. So as the theta gets less, sine theta gets less. I do train my non-calculus students to look at the formula chart to know that, okay? As theta gets less, sine theta is less. And so the denominator is less. So force tension is greater, which is what I said. Gosh, is this the end of this pen already? Is it running out? Geesh, what's with it? Let's have a look. Oh, man, it is out. Oh, sorry, little blue pen. Man, you know where I get all my colored pens and stuff from? Students just leave their stuff in my classroom because they're stupid, and then I just take them. So goodbye, little blue pen. Go to heaven. Okay, the string is cut, and the beam begins to rotate about the hinge. No friction. Sketch alpha as a function of time. So here's the key to this one, okay? You're supposed to think this. Okay, when the hinge is like this, you've got mg and you've got r, and so that's lots of torque, right? And torque equals I alpha, so that's lots of alpha. So we start with a lot of alpha. But then the thing's going to rotate, and it's going to look like this. You still have mg, but you have an angle that is different from 90 degrees. That's less torque and therefore less alpha. And so as this thing rotates more and more, there's less torque. In fact, torque equals RF sine theta. So as the theta changes, the torque changes, and the theta is going from 90 to 180 degrees. So the torque is going to look like sine. What does sine look like? It looks like this. Here's 90 and 180 degrees, right? So the alpha is going to look like from here to here. So it's going to basically start a lot, and it's going to go down, and it's going to look like whatever you call it. It's going to look like a concave down. I think that's the word we're supposed to be using now. Okay, because they teach that in AP pre-calculus. Okay, 4. Wow, this is taking a lot longer than I thought it did. Would a simple pendulum consists of small sphere, hangs from string negligible mass. Top end of the string is fixed. String is pulled to point A. The string makes a small angle theta the vertical. Sphere is then released from rest, swings to the lowest point. The work done on the sphere between points A and B is V. Taken to a planet X. Oh, let's listen to this. The mass of planet X is the same, but the radius is greater. Mass is the same, radius is greater. The sphere is again brought to point A. All right. Released from rest and swings to its lowest point at point B. The work there. Justify why Wx is less than We. So here's what I'm going to say. I'm going to make the following 2 points. Number 1, work done by gravity is the same as mg delta H. It's the same delta H in both cases. But over here, I'm going to say gravity is gm over r squared. That comes from setting the force of gravity equal to the other force of gravity and canceling out the mass of the object that's sitting on the planet, which this would be the mass of the pendulum, leaving the mass of the planet. So same m more r. less gravity. So I'm going to say since gravity is less on planet X, less work done by gravity. Okay, so that's me explaining what I'm thinking there. Okay, a new pendulum is made by hanging the same small sphere from a different string with negligible mass. The new string is slightly elastic, and the length of the string may increase or decrease depending on the tension applied to the string. On Earth, when the sphere again displays theta from the vertical and released from rest, the new pendulum oscillates at the period t on Earth. The new pendulum is then taken to a different planet, planet Y. The radius of planet Y is the same as the radius of Earth, but the mass of planet Y is larger, so that means more gravity. So I'm going to say that in a moment. On planet Y, when the sphere is again displaced from vertical and released from rest, new pendulum, in a clear, coherent paragraph length response that may also contain drawings, not equations, okay? Explain how Ty could be larger, but also could be smaller. Okay, this one got me for about 30 seconds before I figured out what was going on, and that's pretty good. Okay, that's a good hard question if it makes me think for about 30 seconds. Okay, so here's the key: is this? There's more gravity on planet Y, and again we show that with G equals GM over R squared. This is the same. This is more on planet Y. So there's more gravity on planet Y. Now, I'm going to say this. The period of a pendulum is T equals 2 pi radical L over G. So if the string's length is not too different on Y than Earth, right? More gravity, shorter period, okay? But if the string is very loose, right? That's like it has a low spring constant K, like your mother, all right, then the spring stretches out a lot and L increases by a bigger factor than G does. So the period would then be longer. All right, so this one took me a little bit of time. You know, maybe I could write an F equals KX or something like that idea right there. Okay, so that's it right there. So to summarize, there's more gravity on planet Y. More gravity should mean less period, but because the string is elastic, if it stretches out a lot more because of the greater gravity, there's more gravity, so it would stretch out more if it's a loose kind of spring. Then the L increases by a bigger amount, and T, so that should be a so. T would then be longer, be a longer period. All right, well, there's going to be no more of these clear, coherent paragraph length responses starting next year. There is going to be a writing piece on the mathematical reasoning, I think is what it's called, mathematical routines, free response question, and that writing piece will only be worth 3 points, not the 5 that the clear, coherent paragraph length response is. So this is a good one. I didn't write any of these questions, so I'm not tooting my own horn. Whoever wrote this paragraph length response, this is a really good one to go out on. So good for you. All right. Let's see. At time 0, the block A slides along horizontal surface toward block B. The mass of blocks A and B are 6 and 2 and 6. The blocks collide elastically. And as a result, the magnitude of the change in kinetic energy of block B is 9 joules. Determine the speed of block B. I don't think determine now means what it used to mean. Determine used to mean just like give us the answer. Now I think the word indicate means give us the answer. And the word determine is maybe really, it probably should have said calculate here. Maybe determine is a kind of a nebulous word somewhere between derive and calculate. I'm not entirely sure. Okay, so block B gains 9 joules. So I'm going to say kinetic energy is 1/2 mv squared. 9 is 1/2. The m is 2 v squared. So really going to get 18 Oh, no, cancel. 9 equals v squared, so v equals 3 meters per second. Thank you, College Board, for making this a nice number. You're actually following my philosophy on that. Okay, the graph in figure 2 represents positions x of block A and block B, and the center mass, the two-block system is functions of t. Okay, on the graph, draw and label 3 lines to represent the positions of A, B, and the center mass two-block systems from 1 to 2. Okay, so here's what I know. I'm going to do this in different colors, although warning, when they read your free responses, they are read in black and white. So if no one's told you this yet, you teachers out there, do not have your students write in different colors, or they can write in different colors, but when it gets the readers, it's all turned into grayscale. So the green one is, well, we can't tell when it gets to us. You've been warned. Okay, here's what I know for sure. The center mass is not going to change its velocity in any way. Center mass is not going to change velocity in any way. Now, block B, this is the center of mass. Okay, block B is now going 3 meters per second. So in 1 second, it needs to go 3 meters. So that's 1 second, it needs to go 3 meters. Okay, so here we go. This is block B. Okay, and then block A was moving at 2 meters per second. So now I'm going to do a conservation momentum really quick. Okay, mv plus mv equals mv plus mv. Okay, so we basically get 12 equals 6 times question mark plus 6. So the question mark has to be 1. So then, yeah, okay, that checks out. Okay, so that is, there we go. Okay, why does this make sense to me? The reason why this makes sense to me is because for any vertical line that you draw, for any vertical line, the center mass has to be 3 times, school starting, 3 times farther from the 6 than from the 2. So this line has to be 3 times longer than this, because if it's a 6 to 2 ratio of masses, a 3 to 1 ratio of masses, it's a 1 to 3 ratio of distances when you do 2 objects. So again, same thing's happening here. That is a 1 and 3 ratio. And again, here you can kind of eyeball a 1 to 3 ratio. So that's how I know that my graph makes sense. Consider if in the original scenario, instead of colliding elastically, the blocks collide stuck together. Describe how the line drawn for the center mass would change. It would not change, and here's why. The V of the center mass depends on net momentum, right? And I'm going to say the net momentum before is the same in both cases, right? Therefore, the net momentum is the same after in both cases. That's conservation of mass, right? Momentum, I mean, the conservation momentum, right? So the line for V, the center mass, or I mean, not position the center mass, would not change. Okay, well, this was a pretty easy one. I think my students should do pretty well on it. I hope your students did well on it too, or if you're a student, I hope you did well on it. But yeah, there were some pretty easy points here, like this kinetic energy point was pretty easy. There are some good parts, like the paragraph length response, but I can also tell based on what I know about the new way the new AP exam is going to be, that tasks kind of like this and the energy bar charts and the way that they did the experimental design question are really prototyping what the new exam format is going to be. All right, well, thanks for watching.